So I am recording each one of these sessions. I will put it on YouTube. I will send you the address on YouTube so you can see them if you want to go through anything again. I have had some questions through which I will try to answer briefly. One of them was one of them was really quite simple, but it's important, and that was about empirical formulas. When you work out IMDR and you do the moles, so information, then moles, then divide, in the moles and the divide, you do not approximate unless it is really obvious. So if it's 1.998, that's 2. But 1.25 is not 1, you know? So normally the ratio will come out as 1 to 1, 1 to 2, 1 to 3. And therefore it might be 1 to 1.25 or 1 to 1.33, yeah, which you're going to have to multiply up. So when you do IMDR, when you are working out the moles, do not tell your students, do not approximate at all. Well, not, I mean, if it has 26 decimal places, approximate, but just approximate a little. But then use those numbers in the working out, the dividing the ratio to find the ratio. Because quite often, students will get like numbers like 1 and 1 1/4, and they'll go, oh, that's both 1. Okay, that's a question. So thank you. So I'm going to share again. Okay, this is Electrochemistry 2. This is only, I hope will work okay. I hope it will help. At the end, we will have some questions, answers. We can't have too many because I need to go and meet some people from a university, but we can have some. And if people want to send me questions, if you see the guys like Michael and Fatma and Mrs. Kamweru and so on, they can send me emails and I will answer and give you the answers, no problem. Okay? So if there's something that puzzles you, I have no problem in trying to find. I may not know the answer, but I promise I will find it. So yes, and I will show you how to do it. So now we are going to go on with the presentation. I hope we will. Is it working? No. Why is it not working? Come on, come on. Aha, okay. Firstly, a little teaching idea, which I think is good. Some of you will have very big classrooms, very big classes. If you have a lot of people in a class, then it is important to use them in pairs, in 3s, in 4s. On their own, pairs and 4s are better than 3s. This is a very useful teaching idea that I use a lot when I am asking questions of students, and it is particularly at the beginning of a topic. I use think, pair, share. You may know it, in which case, sorry. So you ask them with a question, you say no talking, no hands up in the air, and you say, okay, you have 1 minute to think about an answer. On your own, you can write things down if you want. Then you turn to your neighbor, your pair, or your 4, and that is the show. So think is on your own, then pair, you are working in a pair to see if you agree the answer, if somebody will sometimes have a better idea, and so on. And then they share. Now, if you're working in 4s, you can do the pair twice. So you go think on your own, pair in a pair, and then the pairs pair again. So you now have 4 people working together. And this means that then your classroom is divided into smaller numbers than having 60 or however many. and then they share. So you go round and you ask what they think. This is the bit like, this is the bit called share. What is really important of this is that there is no wrong answer. We, as teachers, it is very reassuring if somebody says, I know the answer, and they've got it right. It is tempting when somebody says something and it is wrong to say, no, that's wrong. We have to say, oh, that's interesting. So tell me why you think that. And then you can see what it is that they have misunderstood, and you can go back and sort that out, and therefore they will get the right answer. So think, pair, share is really good, and it is good not only for making them think, remember, get them to do the work, but the second thing is it shows whether they have understood what you are doing. Okay, here we go, electrochemistry. What we're going to do is this. We're going to look at electrochemical cells. We're going to look at electrolysis. We've done electrochemical cells. We're going to look at electrolysis, predicting the products, both when it is molten or when it is aqueous. We are going to do the uses of electrolysis briefly. I'm going to show you something. And then we'll do Faraday's law about how much product is produced by a certain amount of electricity. Remember, we are doing it like this. I do, we do, you do. Try to focus in, think about what you would explain, what you would then get them to help you with, and then you can hand it over to them. Okay. In explaining this part, they have to know about atomic structure, about ions, they have to learn the formulae of some ions, and they have to know the reactivity series of metals. Reactivity series of metals, this is the one, I think this is the one from the KCSE, but just get one. I always stick it on the wall. I get one, print it out, stick it on the wall, or write it out myself, stick it on the wall. So here is the simple system for electrolysis. Now, why we split electrolysis and the voltaic cell is because it looks very similar apart from what is at the top here. In electrolysis, we provide electricity to make chemical change. In the voltaic cell, these are producing electricity, which we can see with a voltmeter. The problem is that for students, often those two look very similar. And in an examination, they can forget that this is a DC cell, an ordinary battery, power pack, whatever, and they can think they're talking about a voltmeter and etc. So try to keep those voltaic cells and electrolysis separately. How we explain what is happening in here can be quite complicated and quite difficult. I'm going to send you something. Oh, yes, and yes, sorry. And one of the most important things to tell your students is that electrons cannot swim. Now, that seems a really stupid thing to say, but it means electrons cannot cross the either molten or aqueous solution. They cannot cross there. They cannot get across, okay? Now, it is possible sometimes to find a little way of showing. Is this working? Come on. Pick up. Oh, no. Let me see if I can share this. It's not sharing properly. Going to see if I can share this. No. Just a moment. Sorry, just a moment. I'm just trying to get a something synthetic to work. So we'll see if we can make it work. Come on. Ah, yes. Okay. This is a way of visualizing what is happening in electrolysis. I will send you this in the presentation. It allows us to choose metals. So let's make it both silver just for to make it easy. Two silver rods, and let's have a solution, silver nitrate, and it gives you a picture of this. Now, you have to learn how to use these things. So you have to switch the amps up. You have to give it a certain amount of time it is going to run, and then you can run it. Now, what I want you to watch, and this is what I would talk to my students about, I would say watch the masses. So I'm going to switch it on and run it for a minute and then stop it and say, look, what is happening to this one? This is the negative. What is happening to this one? It is getting greater, and this one's getting smaller. So I would then run it for a little while. Okay, so the one which is negative gets heavier, the one which is positive gets lighter. So what's happening? Well, then at the bottom, it has microscopic view, and it allows you to look at what is happening in a sort of simple character way. And what it is this. Let me just stop this just for a minute. So this is the surface of this electrode, and it's the atoms. Let me just move something. It's the atoms. And here comes an ion up to it, and electrons are gained, and it turns into an atom. So this is the idea, is to try to give them a picture of what is happening. Now I'm going to go back and I'll show you something else. So I'm going to reset the whole thing, only this time I'm going to change the metals. So I'm going to have copper on the left, on the right I'm going to have silver, and in my solution I'm going to have copper nitrate. Now what I've got is I've got my copper here. This is the anode. So this is going to dissolve. The copper ions in here are going to plate the silver. So we'll be able to see it more easily. So I turn up the amps, I give a certain amount of time. That's not important. And I turn it on. Now I'm going to look at what's happening at the microscopic area. Okay, so it has a key down here. It says this is the silver, the gray ones are the silver atoms. The small orange ones are copper ions. They should be blue, but it doesn't matter. So I'm going to run it. And you will see the small copper ions come in, and these are all the electrons, and they pick up electrons and become atoms, which are bigger. And so bit by bit, the silver is being coated in copper. Now that might not be very useful, but this gives the pupils a way of understanding what's happening. That's the atoms with their free electrons. The ions come up, gain electrons and turn into atoms and stick to the surface. So this is quite a good way of helping people to understand what is happening in electrolysis. We can look at what's happening at the other one. And in this one, there's the atoms with their free electrons, and they are leaving their electrons behind and becoming ions, and the ions are disappearing. This is why it's getting lighter. Now, to my mind, that sort of visualization is very useful. What I would do then is to draw on the board, like the bottom of an electrode, write lots of atoms in it, and say what was happening in those reactions. Okay, let's move on. Okay, hopefully, yes. So then we have to remember the words, because there are some pretty annoying words in electrolysis. So what I do is I have a couple of things which helps. One of which is in the last thing, there were two cats, and the cats stick together. So here we go. This is what I write up on the board. This is pretty silly, but this is what I write. I write And I say, what charge has a cation got? And they go, I don't know. And I say, yes, you do. Look. So in other words, I always write cation with the T looking like a plus. Or I say anion, anion stands for a negative ion. So this is the easiest. And then you say the cats go together. So this is attracted to the other cat, which must be the cathode. Well, if the cation is positive, then the cathode must be negative. And the anion, which is a negative ion, it must go to the anode, and the anode must be plus. That means that then they've remembered, just by remembering cation, all four of the words, which way round they are. And that's really important. Okay? I always do that, and they find it very, very easy. Then we come to discharge and ion electron half equations. And it takes a lot of practice for many of them. I tend to give them cations first, and I say, all right, how would they become electrically neutral? And sometimes some student will go, well, okay, if I add one electron to that, it can become sodium. And you go, yes, that's right. So this is easy. So I do one, then we do one, and then they do some themselves. And I say, but that's only the cations. So how about the anions? Now, the anions, and it's up to you how you do this, it is perfectly okay to write Cl minus loses electrons and becomes chlorine. Chlorine goes around in pairs, so I need two there, and two there. Or 2Cl minus turns into Cl2 and two electrons. Now you know probably that this is better, but it doesn't matter which one they write. And then you need some practice. Oh, sorry, that's meant to be O2 minus, not O2 minus. This is the only problematic one that people sometimes get a little bit confused by. But if you teach them that this turns into water and oxygen, then they have a chance of balancing it, because already we have three oxygens here. Well, you can't have three here because that would make three hydrogens. So they have to go, that's four. Four of those make two waters, one oxygen, and four electrons. Okay? So that's the equation for the hydroxide. It's the only complicated one that they ever come across. Okay. Here are some slides which I often just show them. I just say, look, in electrolysis of molten lead bromide, this is what happens. I'm not going to stop on these slides because you can see them later if you want to. But I'm just reassuring them that what they're writing is okay. Sometimes I will ask them to write that. And here is the two different ways of writing bromine. Do not give them two ways. You decide which one you want to teach them. Only teach them one of these ways. So either they lose electrons or they produce electrons. They're both the same, aren't they? In aluminium oxide, 3 minus, and the same here. Only teach them one of them, either the electrons on this side or on the products. Then aqueous solutions. Here's hydrogen and copper. And here's chloride and the hydroxide. Now, we're not going to look at those because what we need to do is to be able to predict what is being formed. Now, it is easy because if it is a molten salt, there is only one cation and one anion. Sodium chloride, lead bromide, aluminium oxide. There are only two. That is all that can form. Simple. Aqueous salts, you have to remember there are two cations and two anions. So there is, like if it is NaCl, AQ, then the two cations will be the Na plus and the H plus, and for the anions, Cl minus and OH minus. They must know the reactivity series. And basically, nature goes for the simplest path. So it is easier to discharge hydrogen than to discharge sodium. So it will always go for the lower of the two ions. So the lower cation is discharged, and therefore in sodium chloride, we will get hydrogen. And then in the anions, if there's a chloride or a bromide or an iodide, that is what is discharged. Otherwise, it will be oxygen. So let's have a look at this. Here are some electrolytes. I'll try and make them a bit bigger. There they are. I hope they're a little bit bigger now. Just have a moment yourself to see if you can just confidently say what cations and anions, what will happen at the cathode and the anode. Notice L for liquid and AQ for a solution. So molten lead bromide, molten potassium chloride, aqueous sodium chloride, molten copper chloride, aqueous copper chloride, aqueous silver nitrate, and liquid molten aluminium oxide. So just with a friend there next to you, just discuss and make sure that you can predict what is going to be produced. It's fairly straightforward. Just do have a talk with somebody else. Lean across, make a friend. Yeah, you have friends. I think it's nice that the Kasumu team are about to text me the answers. That's really nice. I think that's what they must be doing with the phone. Ha ha. Okay, you ready? So let's come back down to normal size. Here we go. So in the first one, it's really obvious. It's lead cations and anions, bromide. So it must be lead and bromine, no choice. In the second one, it's got to be lead ions because that's all there is, and therefore the discharge equation will be Pb2 plus 2 electrons makes lead. And here, Br minus, 2 of them because it forms diatomic bromine, etc. Now, if we go through all of these, oops, sorry. What's going to happen in this one is lead and bromine. In this one, because it's molten, potassium and chlorine. In this one, because it's aqueous, hydrogen because that is easier, and chlorine because it's a chloride. That was the rule with the anions, that if you have a halide, it will discharge that. Otherwise, it will be oxygen. Molten copper chloride must be just copper and chlorine. Aqueous, it's copper again because copper is below hydrogen in the reactivity series. Chlorine, silver nitrate, silver very unreactive below hydrogen, and therefore it's silver, and oxygen because there is no chloride. Aluminium oxide, because it's molten, it can only be aluminium and oxygen. Okay. Now the uses of electrolysis I'm not going to go through, but there is plating, electroplating, and it is useful for people to think, oh yes, this is useful. There are some industrial processes. Aluminium oxide, it is useful to have a picture which you can draw for the students, the electrolysis of aluminium oxide with cryolite. The question, what is the name of the other chemical which is added and why is it added? Cryolite is added because the mixture, and this is important, cryolite does not bring down the melting point of aluminium oxide. But a mixture of aluminium oxide and cryolite has a lower melting point than pure aluminium oxide. There's the copper one. You can use these pictures if you want. This is the molten sodium chloride one, etc. And there are other ones. So then we move on to Faraday's first law, which is the calculation. And some people find these quite difficult. They shouldn't be. The first rule is obvious, that if you put more electricity in, you will get more electricity out. Sorry, you will get more product out. The amount of electricity is coulombs. That is amps times seconds. It has to be seconds. If we look at copper being discharged, copper ions being discharged, 1 mole of copper ions requires 2 moles of electrons to make 1 mole of copper. 1 mole of copper requires 2 moles of electrons. Now, 1 mole of electrons is 1 Faraday. You know this, 96,500 coulombs. And therefore, all we have to do, so I would be doing this as my example. I'd say here, what mass of copper will be produced? 10,000 amps, 5 minutes. Okay, so what I have to do, okay, first I need the amount of electricity, but I get the students to talk the process through. So how much electricity in coulombs, in Faradays, how many moles of metal, what mass of metal? That's how I do it. Coulombs, Faradays, moles, mass. Now, some people say CFMM. Have some way of remembering that. Work out the coulombs, how many Faradays is that, how many moles of metal will that produce, and the mass. So here we go. So the amount of electricity, that's the coulombs, is the amps times the seconds. Well, it's 5 minutes, so times 60, that's 3 million coulombs. How many Faradays is that? How many moles of electrons? Well, 1 mole is 96,500. So 3 million divided by 96,500 tells me how many Faradays or how many moles of electrons I have. Then 1 mole of copper requires 2 moles of electrons. So for every 1 mole of copper, I will have had to have 2 times 96,500. Now, I've got 31.09 Faradays. So I will need, that will produce half as many moles of copper. Half as many moles. 2 moles of electrons, 1 mole of copper. 31.09, 15.54 moles of copper. What does that weigh? Mass, that first moles RAM underground. Mass is moles times RAM times 63.5, virtually a kilogram. Let's go through that again. Give them the thought process. Coulombs, Faradays, moles of metal, mass of metal. Coulombs, amps times seconds, 3 million. Coulombs, how many 96,500s? 31. What happens in this reaction? Cu2 plus 2 electrons. Therefore, every mole of electrons will produce half a mole of copper. 31 will produce half as much, 15.54. 15.54 moles of copper, mass of copper, 15.54 times the RAM, 986.8. Okay? Okay, here's one. If you feel like turning your brain on, just go through the steps with yourself. What would you do? What mass of aluminium will be produced by 100,000 amps for 1 hour? Just have a look, think, what would you do? What would you do? 100,000 amps is a lot of electricity. An hour feels like a long time to be producing this. So hopefully it will produce a lot of aluminium. Let's see. So this is what I would be giving to my students. So I would have done one example, then we would have done one together where they can help me. They think they are helping me, they are doing it themselves. They are going to help me do one, and then I would give them this or a simpler one to start with. Here we go. The amount of electricity, firstly, remember coulombs first. 100,000 times 1 times 60 to turn it into minutes times 60 to turn it into seconds, 360 million coulombs. Second, Faradays. How many Faradays? How many moles of electrons? That is the total coulombs divided by 96,500, which gives me 3¾ thousand Faradays. Aluminium reacts because it's Al, let me just remind you, because aluminium will be Al3 plus, so it will need 3 electrons to produce aluminium. So 1 mole needs 3 moles. That's 3 Faradays to produce 1 mole of aluminium. So that's where we go there. So that's 3730 will produce that divided by 3, which will be 1243.5 moles of aluminium. I multiply that by 27 and I get 33,575 grams, or 33.5 kilograms. That's only enough to make 2,000 Coke cans. That's amazing. 100,000 amps, 100,000 amps for an hour only produces 2,000 Coke cans. That's a very expensive way of doing things. Okay, so we have some questions which have come up, but I'm wondering, I'm just going to stop there for a minute and just see if that's okay. So that is predicting the products of electricity, of electrolysis, is quite difficult. The industrial systems are not difficult when you look at them and you work out what is being discharged. Okay, discharged, the ion electron half equations. Then we go into predicting the products is difficult in aqueous solutions. Just remember, at the cations, if you have water, then you have hydrogen ions. The hydrogen ions will be discharged unless the metal is more reactive. Sorry, if the metal is more reactive. For the anions, if we have a halide, that will be discharged. Otherwise, it will be the OH minus, 4 OH minus, 2 waters, oxygen, 4 electrons. So you go through all the industrial electrolysis is quite boring, but it's necessary. They have to be able to draw arrows and say, this is what is in here. It's boring. If you get a chance to do electrolysis in a laboratory, do it. One of the things I am trying to do is, for those of you who do not have good laboratories, I am trying to put together a series of small experiments you would be able to do if you don't have a laboratory, or if you have a very poor laboratory, with very common chemicals. And one of the things I have found is that I could do some electrolysis with a cup, well, a glass, and two pencils and a battery and some salt. And the pencils, I can break the pencils. People go, oh, can't break the pencils, they're too expensive. No, I break two pencils. I get the graphite out of them. I can use that as electrolysis. I get two little bits of wire. I wind them around that. I put it onto the battery. I put some salt into some water. And really quickly, you will see bubbles, only the cathode, because hydrogen is being produced there. But the other one, you will smell chlorine really quickly. So that's the sort of thing we can do, even if we don't have a laboratory. As long as we have some salt, a glass, some water, little bits of wire, two pencils, destroyed pencils, and so on. We can do practicals, even if you are not lucky enough to have a nice laboratory. And to my mind, one of the great things about chemistry was doing experiments, showing people experiments. It's so exciting. And your students will get excited even if you show something in a glass of water. They will think that's great. I smell chlorine. You go, yes. And then the kid who is being very badly behaved at the back, you say, just keep that going and keep sniffing. No, 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 no. That would kill him. So I'm joking. That's a joke. I didn't record that. So just try to make, I will try to make a set of experiments you would be able to do which are interesting. Um, I do them as puzzles sometimes. There's a good one. Let's say you get some raisins, you know, like little dried fruit, and some vinegar and some sodium bicarbonate of soda. And you put the raisins in the bottom of the glass and you put some vinegar in and some water. And then you tip in the bicarbonate of soda. And what happens is it fizzes, okay, effervesces. But the raisins start to go up and down, up and down, up and down. And this is because the raisins go down to the bottom, they pick up some bubbles, the bubbles stick to the raisins, carry them up to the top of the water, they lose the bubbles and they go down. But to show that to your young people sometimes and to get them to try to explain what is happening is really good. Okay, back to my presentation. Okay, so that is the end of electrolysis, really. But I want to show you something that Yesin Thomas showed you at the very beginning. I have sent something to Michael and to Mrs. Kamweru, which is something that you will be able to use. I just want to show you something which you will be able to log on to. I hope you will be able to log on to. I may have to, no, I tell you what, I will share a different screen. I will share a different screen. Okay. What you are going to get access to is this thing. It looks a bit like this. It is something called Quizalyze. And although some of the things across the top will not be very interesting to you, I want to show you how it works. So I'm going to create a quiz, okay? So we've been doing about electrolysis. So what I'm going to do is I'm going to make an electrolysis quiz, okay, a set of questions. And you would be able to do this because you will have access to this. And what it has in the resources is videos and exam questions and all sorts of things. They are not written for KCSE, but they are available to everybody who has this link. In the UK, you have to pay to use this. So I'm going to say I'm interested in electrolysis. Okay. I could even pick the language. Yeah, I could even pick the language. If I want, I can pick Swahili. I'm not going to because my it's not very good. And for year, well, you have to add because in the UK most kids start at 5 or 6 years old. I'm going to go for older. Okay, I'm going to go for older. And here we go. And it starts to generate some questions which I can then add into a quiz. So it's it's just doing that at the moment. It's coming up with some questions. Okay, so I'm going to just add them. So I decide I'm going to use them. I'll show you what happens in just a minute. It'll only do me a very few. What happens to the ions in an electrolysis solution during electrolysis? They migrate. The answer is being shown underneath. Now, your students would not see this. So I'm now going to put all of these. This is just showing you one of the things that this can do, this sort of software can do. Now, okay, you do have to have quite a clever phone, or you have to have a computer, laptop, but let's hope that's it. Okay, so let's just add them, and let's have a look at the quiz. So I'm going to save it. And now I can show myself, I can see what this is like. Okay, so I'm going to imagine I'm a student. So now I have just very, very quickly said something on electrolysis. So I'm going to just do it very simply, like a classic quiz. Here we go. And hopefully, here we are. So you could then do this in class. So I now have this is the question, what is the main purpose of electrolysis? And I could get them to think about it. I could get them to shout out answers, whatever I want. What is the main purpose of electrolysis? Oh, 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 oh. So I've got this right. Now that one of the questions, well, one of the answers if we went back would be to make electricity. That's the confusion, electricity and voltaic cells. So each one of these you could, if you have a projector, you could actually project it and show it. The whole class could see it. What happens at the anode? Ah, yes. Okay. Let's say we know it's not dehydration. Let's have a look. So I'm going to say dehydration. Uh-oh. I'm stupid. So it's not dehydration. Have another go. Oil rig, oxidation is what happens at the anode? Cation is positive, cats go together. Anode must be positive. So how about this? That's it. Okay. So I can run this in a lesson. I can do this in the electrolysis of water. What are the products formed at the electrodes? Carbon dioxide, hydrogen, ozone, hydrogen, hydrogen, oxygen, sulfur, oxygen. Hopefully your class would say hydrogen, oxygen. Yes, I'm genius. Now, this is the sort of thing, if your students have their own phone, they can actually do this themselves, and they get very competitive trying to become faster and faster at this. What happens at the cathode? Reduction. Okay. Now we can lead it, we can put it, we can get the wrong answer. What is a common use of electrolysis? Baking bread. If you bake bread when you're doing electrolysis, you are an idiot. Maybe washing clothes? No. Generating heat? No. Electroplating? Maybe. Yes. And it says here, it gives you a little bit of the answer if you get it wrong, and so on. Okay. So this is, wait a minute, let's go back. Whoops, not that one. So this is one part of this particular piece of software, okay? But as I said, there are other parts to it, and you're going to get the access to it. So let's say I want to look at something else. I'm going to find some resources, and it says 70,000 quizzes, slides, in other words, pictures, worksheets, and videos on anything I want. So let's say I'm finding on atoms. Okay, I'm going to find out about atoms. Now, if you can remember that you add 5 or 6 to the year, then this is for 13-year-olds. So maybe if you've got a class of 13-year-olds, you might say, okay, I'll look at this. And in most of these, they have a little starter quiz at the beginning to see if they already know it. Then there is a worksheet which they can do, which you can actually print out one version or show it on the board. There is a presentation, which is somebody will go through it with you. So there is a presentation which goes through, yeah, this is what you are meant to be able to do. This is for 13-year-old. Here are the key words I need to know, and so on. So in other words, it is a series of lessons almost. There is the quiz, there is a video where you can watch somebody else doing it, and so on. And this is huge. I mean, I don't know whether you would want to use it or not. And you can build up your own library, and some of you may even want to use classes. So you can put all your names of your students in the class, and then you can collect their marks. So this is what is called Quizalize, this thing. It allows us to do things, and you're going to get it for free, which is pretty good. So that's me. That's just about me. Now, I had a couple of questions which were sent to me. I could show you them very briefly. Would you like to see them? I know one person who would like to see them. Let's see if I can find them, and therefore we can share them. This is a question. This is an energetics question. Here we are. This is an energetics question. It was this. This is hydrogen. I'll try and make it a little bit bigger. If you look at this, come on, move. Oh, there we are. If you look at this, this is hydrogen molecules and oxygen molecules reacting. The hydrogen has its bonds broken first, then the oxygen is atomized too, and then it makes water as a gas, and then water as a liquid. Remember that in any one of these scenarios, anything going upwards is endothermic and therefore positive. Anything coming downwards is exothermic and therefore negative. The question asks which delta H values will have a negative sign. That's anything coming down will be negative. They're always exothermic. Second one, what name is given to 1, 2, 3, and 4? One is breaking the bonds in the hydrogen. If you just look at what changes, H2 turns into 2H. So that's the enthalpy of bond, or bond enthalpy for hydrogen. In the second one, the oxygen is produced as this is a mistake. What this should show is just O, not half O2. It should show just O, and that's atomization. This one here is, in this one here, this is the formation of H2O as a gas, and that there is from gas to liquid. That's the liquefaction. That's the reverse of boiling, isn't it? If you look at it, it's condensation there. What physical change is being represented by 4? That's the one that's turning from a gas into a liquid, so that's condensation. In terms of 1, 2, 3, and 4, give the overall enthalpy change for hydrogen burning in oxygen to make the liquid. Well, it sounds a little bit funny because it looks like some are going up and some are going down, but basically it's 1 plus 2 plus 3 plus 4 because this value here is, I can't remember. It's about 300 kilojoules. No, about 600 kilojoules. So it's this one plus that one. That one is endothermic, endothermic, exothermic, exothermic. You notice this one is below that. So the difference between this one and that one there, can I draw on this? Can I draw on this? No, I can't. Oh, okay. From here, up here, down to the bottom, that's the delta H of formation of the whole thing. So you just add them together. Some are positive, some are negative, okay? So if you email me questions like this, I should be able to help. I hope I would be able to help. After 42 years of teaching, I should be able to help. And there was one other, where is it? Can I find it? Ah, this was an organic question. I'll make it bigger because that's almost invisible. There it is. What we've got is calcium carbide, ethyne and compound B, ethyne, chloroethane, ethene, and ethanol, the alkanol. Okay. And it asks you, this question asks you about all these different steps. I don't have time to go through all of it particularly, but I'll tell you what happens in them. So from calcium carbide to ethyne, we just add water. It's really simple. We'll just add water. But now we have in here ethyne and calcium hydroxide, and we have to separate them to make it into ethyne. That's simple evaporation. From ethyne into C2H5Cl, it wouldn't normally form C2H5Cl. One of the sadnesses to me is that when I look at KCSE examination questions, they quite often have errors in them. So if you reacted ethyne, C2H4, with HCl, it would not produce C2H5Cl, it would produce C2H4Cl2. So actually step 6 would be with hydrogen to make it into ethene and then hydrogen chloride to make it into into chloroethane. Step 2, from ethyne to ethene, we're just adding 2 hydrogens. One of the most useful things you can do with your students when you're doing this sort of question is to make them count the atoms. So here we have C2H2 and C2H4. Oh, there are 2 more hydrogens. So step 2 must be adding hydrogen. That's simple. Adding hydrogen, I use nickel and about 70 degrees Celsius as a catalyst and hydrogen gas, and it does that. Step 4, from ethene to ethanol, that's pretty easy, really. That's adding water. If you just add up C2H4, C2H5OH, I've added H2O. So this is steam. If it's industrial, it is 300 degrees Celsius, 70 atmospheres, and water and a phosphoric acid catalyst. So these things are fairly straightforward, okay? But if you need to send me questions, you can. But that's basically the end of my life. No, my work today. I hope that it has been useful in some parts. I hope. Actually, something just struck me. I just want to not blur my background. I tell you, I'm in my wife's office, okay? She has a nicer office than I do. And you know what Yestin Thomas at the beginning said? You have to work hard to do things. And sometimes you work and you do not know whether you can do it. and you struggle and struggle and struggle. Behind me is a set of medals. Okay, these are medals which my wife won by running. Okay, when she started, she was very poor runner, and she ran and she ran and she ran and she ran and she got fast. That's it. That's all you got to do, guys. Seriously, I'm impressed by her. I can't catch her, you know. No, go run. So, but if you can train your students to believe that there is nothing wrong with not knowing the answer, nothing wrong with it. You do not get anywhere by repeating the things you can already do. Yes, I can already scratch my head. Whoa, I must practice. Wait, look, I can do it. Hey, it is very tempting for students to repeat the things they can do, not the things they can't do. Get them to do the things they cannot do with your help. Okay, I'm going to stop recording.